So today we're studying particle motion, graphs, graphically. And we utilize this graph right here. So this is the graph, and this is the graph of velocity. So this is a y equals v of t versus time. So take the time to draw that graph. This is what we're going to use in reference for the majority, I believe almost all of our class today will be based on this graph right here. Okay, so you'll see in your homework you're just given different versions of a graph that looks just like this. So please take the time to copy it down. So what we have here is a graph of velocity, and it should be noted that we read this graph. I don't even realize how much the top part was. We read this graph much the same way that we read the graph or read the sign charts. Um, so as such, values above the x-axis represent positive velocities. And I feel like, I am explicitly telling you, but there is confusion about this. Values below the x-axis represent negative velocities. And of course, as we've learned in our lessons this week, positive velocities represent moving forward. So you could say that values above the x-axis represent moving forward. But first off, it's kind of like this means this, which means this. All right. And values on the x-axis represents, um, v of t is 0. It's at rest. As we should remember, acceleration is equal to the derivative of velocity. Graphically, the derivative is represented as the blank of velocity graph. So what is that blank? So, sorry, I said the derivative. Yeah, I'll leave it as derivative of the graph. So what is the derivative? What is the relationship when I say derivative? What is another meaning for the derivative? How can we find a derivative by looking at a graph? What is the derivative? Anybody?
It's a slope.
It is the slope. Perfect. As such, these graphs of linear piecewise functions slope is calculated as A of C is equal to velocity at B minus velocity at A over B minus A, for A less than C less than B. In other words, here's what I'm saying. Okay, you're like, well, what does that mean? The acceleration at a point t equals C is found by finding the slope of velocity graph from two known points for which t equals C is within. I just want to be very explicit in what I'm saying. So if I want to find the velocity at 2, for example, so one of the questions I'm going to ask you today is, we want to find the velocity at 2, right there, at time equals 2, okay? We want to find the velocity right here at 2. So we know the velocity at 1, and we know the velocity at 3, because the value 2 lands right on this line. Just like your other algebra classes, if you can find the slope of that line, then what you've technically found is you found the acceleration. You found the derivative of velocity at 2, all right, versus the value of it, the value of velocity. Quite a bit already covered here. And I'm going to ask you the same questions that you were asked yesterday. Basically, all of the questions that were asked. I'm not asking you any really new questions. Moving forward, moving backwards. What is the acceleration? When is a particle at rest? When speeding up, slowing down? These are all the same questions that we answered yesterday. So we know the relationships already. We know the relationships between velocity and acceleration. And we're doing it. And so let's do that. We're going to using the graph above. So using y equals v of t shown above. A. When is the particle moving forward? Justify. Okay. So here's my velocity graph that I was given. So the question is, when is the velocity moving forward? When you look at this, it takes a specific practice. It takes practice. All right. A individual who hasn't learned, who hasn't mastered what we've already done this week, will say, for example, 6 to 7, and that's it. They only think 6 to 7, or those things, something like that, or they might even say 4 to 5, which would be very wrong in terms of 4 to 5. Before I show you and explain to you why, what is the answer? When is the particle moving forward? And here's my hint to you. I always like to write the justification first. So when I see moving forward, I think what? What is the justification for a particle moving forward?
V of t is greater than 0.
So if you write that, moving forward means the velocity is greater than 0. Now when you look at the problem, now you're looking at just like an algebra one. Like that's the calculus, basically. That's the calculus. The calculus is moving forward is when velocity is greater than 0. Done. That's calculus. Now it's just algebra. Now it's algebra 1. I gotta have a graph of velocity, and I want to know when that graph is greater than 0. Because that means moving forward, which I already did. I already found that. That was the calculus understanding. What is the answer?
Would it be 0 to 1? 0, comma 1. Union with 6, comma 8.
And that's my answer.
Oh, mister. Would it be bracket at the beginning when it's 0, or would it be parentheses?
Technically, it would be bracket. One of the rules in calculus is that, and I basically want you to use parentheses. I always want you to pretty much use parentheses. The technicality part of it would be bracket, but on the AP exam we accept parentheses. All right. If it's supposed to be a bracket but you use a parenthesis, you get full credit. However, if you use a bracket when it's supposed to be a parenthesis, you lose credit. So it's just better to use parentheses, in other words. Most of these problems might say, typically the problem will say something like t greater than 0, less than 8. So if I did this actually will help me, meaning that I'm not going to include the endpoints at all. So most of the times when we do these type of problems, we don't count the actual endpoints on that. All right. Does that make sense? Or it might say like this. So yeah, if you were to use a bracket, Ariana, you would get credit. If you were to write your answer like this, you would get credit.
Okay.
Okay. B. Oh, so when I look at this graph, I can think of it like this. I can say, oh, okay, so the velocities are positive right here. If I was thinking about how the sign chart is, and the velocities are positive right here. Velocities are negative right here. All right, I can actually think about it in terms of the signs, that if I were to make a sign chart, it would go positive, negative, and then there's actually a weird, it's actually zeros for right here. It's a big long 0 right there, and then positive. B. When is a of t, when is acceleration positive? Now I could also say, when is velocity increasing? Now this is a question that does get asked. Justify. This is different than speed. You can't hear me? Okay, thank you. So the question here is, when is acceleration positive? Okay. Now I'm asking you, when is velocity increasing? Okay. When is velocity increasing? That's another way of saying it. What When I say acceleration positive, what am I really asking you? What's the justification? Acceleration is the what? What is acceleration in relationship to velocity?
It's the derivative of velocity.
So I want to know when the derivative of velocity is greater than 0. The calculus means that, or sorry, I'm pointing to the wrong location. This is the slope of v of t. So I'm asking you, when is the slope positive? When do I have a positive slope? Anybody? When does this graph have a positive slope?
When it's greater than 5.
No. Is this a positive or negative slope?
Positive.
That's a positive slope?
Oh, wait, it's going down there.
Yeah, it's negative. What about this slope?
Negative.
What about that slope?
Constant.
What about that? No, it's 0. It's not constant. It's 0.
Oh, yes. Yeah.
Constant and 0 are two different things. 0 is a constant. Constant means a lot of different things. -5 would be a constant. Technically, that's a constant slope. Everything here is constant slopes. What about here?
Positive.
So I have a positive slope right there. So that means one of my answers is 4 to 5 because I have a positive slope. I'm not looking at the value. I'm not looking above or below. I'm looking just at slopes. And then what about that slope?
6,7. Oh, that's 0.
0. What about that slope?
Positive.
Positive. So union 6,7. I am looking at the slope. Don't overthink it. You're just looking at, I'm literally asking you, if I gave you this graph and I said, where is the slope positive? You don't look at, it doesn't matter if you're above or below the x-axis, or the t-axis in this case. You're just looking for slope being positive or negative. C. When is the particle at rest for more than an instant? So when is the particle, now when is a particle at rest? So here's the calculator, or taking its physics. When is a particle at rest?
When v of t equals 0.
Okay, and we want to know when its velocity is equal to 0 for longer than an instant. And this is a very common mistake. This problem right here is often very commonly mistaken by many students when they're first doing this, okay? So I want you to think, don't just wait for an answer. Think about where you think the answer is. We're going to go over what the answer is right now, because if you make this common mistake, it's okay. We're just learning it. But then you got to wipe it off of your skill set, you know, not to make it a mistake again later on when we're actually doing these problems. So where do you think velocity is 0 for more than an instant? And now can I get an answer?
From 5 to 6?
From 5 to 6. What is the common mistake people will say? Can anybody think they chime in? What is the mistake? What is the incorrect answer?
3 to 4.
3 to 4. This is a very common thing. A lot of students will think from 3 to 4 we're at rest. We're not. Velocity is negative from 3 to 4. What is constant, or what is 0, is acceleration. Acceleration is 0 from 3 to 4. Acceleration is also 0 from 5 to 6. But the velocity itself is negative. So we're just moving backwards, but we're not speeding up, nor are we slowing down from 3 to 4. We have constant velocity. And this is where I was saying with Ariana earlier. Velocity is constant from 3 to 4. It's not 0. Very common when we first do these type of things to get that. D. Find A of 2. Explain. Show your work is basically. So I guess I have to redo it again. So we're going to find A of 2. I mentioned this earlier. Right here. Time equals 2. All right. So that right there is T of 2. All right. Let's find it. So that means I have to find the actual value. So how do I find A of 2? A of 2 represents the slope of V of t at t equals 2. How do I find the slope? Well, it would be the derivative, but we don't have an actual function. So I'm not going to actually do a derivative and plug in. When we were doing the work yesterday, you had a function, you found the derivative, and you would just plug in 2 into that derivative, right? That's what you did yesterday. But I have a graph, and I mentioned it earlier on in the notes.
Isn't the V of B minus V of A all over B minus A?
Perfect. But what is A and B?
Is it 1 and 3?
Correct. I'm only looking at this segment right here. I just need to find the slope of that piece right there. So what's the slope? So it's 1 and 3. So to find the slope, I'm going to find V of what? Let's put the two materials together. Ariana told us kind of like the formula. Nicola told us the values of A and B. We can put them together now. V of 3 minus V of 1 all over 3 minus 1. Now, we call this the quotient. So on the AP exam, one of the things that when I'm I don't grade the AP Calc, I grade AP Statistics exams. But what the graders do when they look at the AP Calculus exam is, did they show the quotient? So that's how you have to show your work. You have to actually show what you're subtracting, and you have to show that. Now you can actually put in the numbers there, or you can utilize this notation, but it must show you using the quotient. So A of 2 is equal to, what is V of 3? What is V of 3?
Is it -3?
It is -3. Minus, what is V of 1?
0.
0 all over 2, which gives us
-3/2.
Perfect. Now, let's say, and I didn't put this earlier on, let's say that this is in meters per second. Okay? And I say, like, indicate units. So if velocity is in meters per second, and actually I'm going to go do that to the very top. This is in meters per second. If velocity is meters per second, then what are the units for acceleration?
Meters per second squared.
Perfect. E is the particle speed increasing, decreasing, or neither at t equals 2. Explain. Okay. When I see speed increasing, decreasing, when I read this, when I see speed increasing, decreasing, I need to think of what? Thank you, Ariana. When I see speed increasing, decreasing,
V of t and accelerate a of t.
and I'm going to add one more, v of t and a of t, signs, right? The signs of v of t and a of t. I don't need to know the actual value. I just need to know the sign. Ooh, we already did one. We already did part of the work, right? We now know from our previous problem, and the reason why, we know a of 2 is positive or negative. Negative. Okay. What about velocity? At 2.
Negative.
Why?
Because it's below the x-axis.
And the acceleration was negative because we have a
negative slope.
Okay. So now taking that piece of information with what we learned yesterday, this is the explanation. Okay, so that's the explanation. So, but what's the answer? Is the speed increasing, decreasing, or neither?
Increasing. Speed increasing.
And just the speed increasing, and actually we do still need a because.
Because V of t and a of t are the same signs.
Perfect. We have one more type of question. It's the same follow-up to this right here. Oh, I'm just going to state this one verbally. When does the particle change direction? Let me write that down then. There was a pause there.
Isn't that t equals 1 and t equals 5?
The answer here is actually only one of those ones. It is only t equals 1. Why does the particle change direction at t equals 1?
Because vt signs changes.
So the answer is only t equals 1 because that's where the velocity changes. A lot of individuals would answer about this 5 or 6, like, well, it does change direction, but when we talk about changing direction, we're really referring to at that instance. Don't worry, I've never seen an AP exam problem. Ask that question when you have a graph that does what happens between 5 and 6. I've never seen the AP, because there is some confusion, and some teachers were like, well, does it change at 5 or does it change at 6? And there could be a lot of misinformation in defining that. The real answer is 1, because we're talking about more specifically, when does it go whoop, whoop? You know, it only stays constant for a rest for an instant and then it changes. So you won't see that type of graph. You'll see them go through the x-axis if the question about changing direction does show up on the exam. But I just wanted to throw that in there. All right. Speed. Our last thing is on a speed. We learned that speed is the absolute value of velocity. So technically, if this is the graph of velocity, then the graph of speed is the absolute value. So that means it goes like this. So all of the positive parts are still the same. So that's what speed looks like right there. But with speed, instead of going to 3, -3, it's going to come up to right here and right here. And so the graph actually looks like this for speed. So speed is just the absolute value. So technically speed is the bouncing part up. So I just do want to note that. What is the maximum speed? Can anybody tell me what the the largest value of speed is? In this graph? What is the largest value of the graph? What is the largest y value?
4.
4. So the maximum speed is 4. It occurs right there. But now if I were to ask you when is speed increasing, you would tell me when the slope of the speed graph is positive, right? Speed increasing means that the slope of speed graph is positive, which happens right here and right here. Do you see how on this graph of speed the slopes are positive here and here? Does everybody see that? Oh, I guess. Yeah. Okay.
Yeah.
Now, we are not going to look. Some people do that. Some people will trace the speed graph over there. I don't like to do that. So if we were looking directly and this is typically a physics trick at velocity graph, A of t and V of t are the same sign when the graph is moving away from the x-axis. In other words, if it was below and moving away, equals V of t and A of t, both negative. What I'm referring to is this part of the graph right here. You see how the velocity, the graph is moving away from the x-axis. If we read it from left to right, it's moving away from the x-axis. This is a quick just way, like, oh, acceleration, negative slope. Acceleration is negative, and velocity is negative right here. So all this part of the graph, both velocity and acceleration are the same sign. Same thing is true over here. Velocity and acceleration are the same sign. They're positive. And how does that look graphically? Because they are both positive. It's moving away from the x-axis. And the opposite is true, of course. A of t and v of t, opposite signs when graph moves toward the x-axis. Now, on a multiple choice problem, you can just say, I look at the graph and say, oh, we're moving away or moving positive, and because you want to move on to the questions as fast as possible. It is technically not the way that we should be answering our calculus questions, and if we have to justify, we never justify in saying the graph, like that would not. We'd have to say the signs of acceleration and velocity. So, for example, in this last example, or I guess F, example G, when is speed increasing and decreasing justify? And we're looking at we're not going to look at the speed graph like we did before. We're just going to be looking at our velocity graph right here. So when is the speed increasing? When is the graph moving away from the x-axis? Or when is velocity and acceleration the same sign? When are they both negative? When are they both positive? Are we moving toward or away from the x-axis? Right here. Toward. So that's not it. Are we moving toward or away?
Away.
Away. So does that mean speed is increasing or decreasing?
Decreasing.
Increasing. So from 1 to 3, speed is increasing. Now remember, what I could do if you don't like this moving away or towards, what you can do is you can actually just, oops, you could, if you want to, show the bouncing graph, and now you can see you're just looking at the slopes like I did earlier of this new graph that I've overlaid on top. We're only looking at, so we're looking at positives for that one. So if you can see from 1 to 3, that was a very poor version of me drawing that part of the graph. 1 to 3, the graph has a positive slope for speed. Union, where else?
Would it be 6, 7?
Correct. And the reasoning, because V of t and A of t, same sign. Now, right here, A and V are both less than 0. Here, A and V are both greater than 0. We do not need to explicitly say both negative, negative, positive, positive, because we're just doing from the same sign. When is speed decreasing? Well, visually, looking at the velocity graph is when the graph is going toward the x-axis. Analytically, when velocity and acceleration are opposite signs. So, acceleration is positive. We're above the x-axis, but I have a negative slope. So this is a negative positive. Negative velocity, positive velocity, negative slope. I'm also moving toward the x-axis. So speed is decreasing from
0, 1.
Union Okay, that doesn't work. That doesn't work. Oh, right there. I'm moving toward the x-axis. I always use the toward the x-axis to first identify and then I justify in my head. So I'm moving toward the x-axis here. Why and what does that mean? It means I have a negative velocity because I'm below the x-axis, but I have a positive acceleration because there's a positive slope. So union what?
4,5.
And am I done?
No, we got one more.
Got one more right back over here. Another one that was just like the very first one. So I have here, here, and here where velocity and acceleration are opposite signs. The ones on top, velocity is positive, acceleration is negative. The one on bottom, velocity is negative, acceleration is positive. So union 7 to 8. And the reason is because V of t and A of t opposite signs. And that's what I have. That's our first major introduction to particle motion. We will elaborate as we learn more calculus concepts. We could introduce other advanced functions. We're not going to do that right now. We have to learn some more theorems and stuff. And so you'll see me introduce more particle motion into some later topics. But for this unit, this is the last of the pieces that we need to understand. Using the graph should be, hopefully you should feel that it's easier than using a function. Some students don't prefer the function and think that actually the functions are easier because it's very analytical. Most of you are taking AP Calculus because you have very strong analytical skills. Here's a function, plug in, those type of things. Whereas when we're reading graphs, although for the most part, some of the students would, typically students who don't reach calculus find reading graphs a lot easier than working with functions. So, you might be on the opposite spectrum of that. But it's the same questions. The information is just presented differently. Instead of presenting it as a function and then plugging in to find the values, you can read the values and the slopes directly onto the graph. That's what I have for you today. As a reminder,